Hello, my name is Hunter Bennett, and I'm with Alexander King and Richard Hartnett, and our project is over weirs. First, what are weirs? Weirs are essentially a small-scale dam built across a stream or river to control the height and flow rate of water. This can be used to prevent flooding or measure water flow on a smaller scale. Weirs are usually made of concrete or steel. This led to our problem statement: how does weir shape affect flow height and flow rate? Our design for this project includes a water container, which will contain enough water to get consistent flow for a longer period of time. The container is then flipped to the orientation shown in the photo, which allows water to flow through the channel and get consistent laminar flow through the weir and into the drain. We can then measure the change in height of the water using the measuring marks, which will allow us to measure the flow rate. The weir is also replaceable, which will allow us to change the shape while keeping everything else consistent.
Here's a brief overview of the math for our demo. Let's first discuss the flow without a weir. So using Bernoulli's equation from point 1 to point 2, we can find the velocity at point 2. We make the free surface and large container assumptions so these two terms cancel out. And at point 2, it's a free jet, so the pressure there is also 0. After a bit of algebra, we get that U2 is equal to 2g times h minus y, which is also given by Torricelli's law. By integrating that velocity over the area, we get that Q is equal to this expression without the weir. The math with a weir is very similar, same Bernoulli's equation, but the only difference is that instead of integrating from 0 as our lower bound, we're integrating from the height of the weir to the height of the flow, which gives us this slightly different expression for the flow rate over the weir.
Our first experiment was our control volume, where our weir height is 0. Each black mark that you see and the space between those marks are 1/8 of an inch. The height of the water when undisturbed in our experiment was found to be 1 inch. Our second experiment consisted of a broad-crested weir. A broad-crested weir consists of rounded edges, which tends to be used in irrigation and drainage systems. Our experiment consisted of a weir height of 1/4 of an inch, which led to a displacement of 1/8 of an inch above our control. Our third and final experiment was a sharp-crested weir. The sharp-crested weir consists of sharp edges, which displaces the water higher than our broad-crested weir. Sharp-crested weirs are mostly used to measure small flow rates. Our experiment found that our sharp-crested weir, at the same height of our broad-crested weir, displaced water about 1/8 of an inch greater.
Here are the results of our experiment. Without any weir, the water flowed at its maximum rate with a height of 1 inch. The rectangular weir reduced the flow rate by about 14.7% and increased the height to 1.25 inches, whereas the rounded weir only decreased it by about 13.8% and increased the height to 1.125 inches. This experiment showed that the design of the weir significantly affects the flow rate and the water upstream height. The rectangular weir restricts flow more and causes a higher buildup, whereas the rounded weir offers a balance between reducing the flow rate and minimizing water height changes.